Okay, here's warm-up 6.4. We're going to write this in log form. So to write an equation in log form, first just write the word log. The base here is a, so the a is going to the base is a little footnote in log form like that. It's right below log, okay? And the point of log form is that it isolates exponents. So the exponent in the original equation in the exponential form is going to get isolated. The b then gets isolated. So I'm going to leave this little space and I'm going to say this is going to equal b. And then the c, there's only one spot left for it. That's going to be the contents of the log, also known as the argument. And it's really important to just memorize where the pieces go so that you can convert into log form, and also that you can convert from log form into exponential form. Okay, so looking at this next one, d is the base, the exponent is the isolated piece, so d to the f is going to equal e. There's only one spot left for the e then. Okay. All right, let's evaluate these. So you can put these all into a calculator, but let's see if we can evaluate these three without a calculator. So if you understand what a log means, evaluate means what does this equal? So I'll just put x. I want to figure out what x equals, right? Well, if I convert this to exponential form, my base would be 2, my exponent is x, and this is 16. So then I'm thinking 2 to some power equals 16, and I can do that in my head. 2 to the second is going to be 4, 2 to the third is 8, 2 to the fourth is going to be 16. So that means x has to equal 4. Right? And I'll get back out how you can put that into a calculator as well. Okay. This next one is a common log because there's no base written, and when there's no base, the assumption is we're dealing with base 10. Okay. So if I'm using the same technique, 10 to the x is going to equal 10,000. And then, well, if you just count up the zeros, there's 4 zeros, so 10 to the fourth is going to be 10,000. So this log is going to equal 4 again. Okay, and that one, if it's base 10, you really could just type log 10,000 in your calculator. So log 10,000. So the log button is right here, right? And you hit enter, 4, right? If you had, it's the same as the number of zeros when you're in base 10. All right. All right, this next one is a little tricky, but let's try to set it up. If this is equal to x, now I have 125 raised to the x equals 5. And it's a little weird because you're taking a bigger number, raising it to an exponent, and it's becoming smaller. Well, that's going to happen when we have a negative exponent, okay? So when I'm looking at 5 and 125, I'm thinking, oh, 5 to the third is 125 because 5 quarters would be $1.25, right? So 5 times 5 times 5 is 125. Well, so what I can do is think of this as, this is, I said a negative exponent. I meant it's going to be a fractional exponent. So what I can do is, instead of raising this to the third, I want to really take the cube root of it. And taking the cube root of 125 is same as raising it to the 1/3. Okay, so that means x would have to equal 1/3. So that's what this log equals. Okay, and that one's a little tough. So I'll come back to that in just a second. But let's look at this one. So this one's not base 10. So in some calculators, if you hit the log button, it'll let you put in your own base. So there'll just be a little cursor there, and I could put in the 7. This one doesn't do that. So what I'd have to do here is use change of base. So change of base, I can write this log in base 10. The way it's going to work is with a fraction that looks like that. Okay. So I often see people get these this flipped upside down. So you see how the 13 is higher up than the 7? So that means log of 13 is higher up than log of 7. That's how I remember that. Okay. And now I can type those, both log of 13 and log of 7, into any calculator that can do logs, because they all have base 10. All right. So I'm going to type log of 13. And you could do these piece by piece, but I'm going to just do the division on here. Make sure you close the parentheses there before you take the log of 7. It doesn't really matter if you close the one on the bottom because nothing's happening after it. But if I didn't put that parentheses in, it'd be taking the log of 13 over log of 7. That's not what I want. I want the log of 13 over the log of 7, and that's going to give me about 1.32. Okay, so we could have done the same thing here, so let's try this. This would be log of 5 over log of 125 for that previous problem. I close the parentheses there. And hey, 1/3, 0.333 is 1/3, right? So same result there. Okay, and you could have also used change of base here to get this one. Okay, all right, let's we're going to find the inverse on these two problems. This means the inverse of function f. So what I'm going to do is switch the x and the y. If I think of f of x as y, let's switch the x and the y. Okay, and then my goal is to solve this for y. I need to get y isolated. So we can start with the 3. Some people try to put this in log form right now. You don't want to do that yet. Start by subtracting 3. Let's isolate y as much as we can with our old algebra techniques. And then we're kind of stuck when we're with our old algebra. Taking the square root's not going to do me any good. Then I'll just have the square root of 7y. So that's not going to work. And even taking the like y root of both sides, that doesn't really mean anything. Okay. So I have to put this in a log form at this point. So in log form, my base is 7. The exponent gets isolated. That's what I wanted to happen. I wanted to isolate the y. And then the contents of the log is going to be the quantity x minus 3. And it's good to use parentheses to show that the negative 3 is inside the log, because it would be different if you had like log base 7 of x and then subtracted 3 afterwards. That shows clearly what part is inside. And then I'm just going to put this back in function notation. And there is the inverse of that function. So notice when we had an exponential function, the inverse is a log. That's always going to happen. Exponential functions and log functions are inverses. So this really is a log function here. This is going to be log base e. It's my natural log. So I'm thinking, okay, it should end up looking like an exponential function. Let's see what happens. So I'm going to switch the x and the y. Okay, and then I want to isolate the y as much as I can. Since the negative 9 is not inside the log, that means I can add 9 to both sides, and that's what we want to do. So x plus 9 is going to equal the natural log of y. Okay, and then I have to get that y out of the log. So I'm going to have to convert this, and you also have to know that natural log means log base e of y. Okay. So now converting this into exponential form, my base is e. The isolated part in log form is the exponent, so that means x plus 9 is going to be the exponent, and then the y is isolated now. Okay, and now I just put it back into function notation. And there we go. So when we have a natural log, the inverse of that is going to be an exponential function that involves e. That's always going to happen as well. Okay? All right, that's the end of the warm-up, and I'll see you next time.